Hello there, and welcome to Sleepy Science Vault. In the beginning, there was a cloud. A vast, slowly spinning cloud of gas and dust drifting through the early galaxy, ancient beyond measure, cold and patient and unimaginably large. And for a time, it simply existed, turning gently in the dark, holding within it the raw ingredients of everything that would one day become familiar to us. But in the universe we're exploring tonight, something different happened. Or rather, something did not happen at all. The collapse never came. The ignition never occurred. The sun never formed. And with that single absence, everything changes. Without a star at the center of this story, there is no nuclear furnace pouring energy into the surrounding space. The cloud of material that might have become our solar system simply never finds its anchor. There is no gravity strong enough to pull everything inward, no central body to organize the chaos, no quiet heartbeat at the middle of a planetary family. The sun, had it formed, would have contained nearly all the mass in the entire solar system, about 99.8% of everything. That is not a small detail. That is the foundation. Without it, there is no organized system at all. There are no planets in neat elliptical orbits. There is no structure. There is no home. The material that would have become Earth, Mars, Jupiter, and the rest, it lingers. It drifts. Some of it might slowly clump together under its own weak gravity, forming dark, wandering bodies with no star to orbit and no warmth to receive. But they would not become planets as we understand them. Not really. They would be orphans moving through empty space in more or less straight lines, following the simple physics of objects with nothing pulling them home. Even the asteroid belt, that ring of leftover rocky material sitting between Mars and Jupiter, would not exist in any recognizable form. It is part of the solar system's story, a record of material that never quite finished becoming a planet. But without the sun's gravity shaping that story from the very beginning, the whole narrative simply doesn't take place. What exists instead is quieter, darker. A region of space that looks, from a distance, almost exactly like every other cold patch of the galaxy. Now, let's allow ourselves a thought experiment, the kind of gentle, wandering question that late nights are good for. Suppose, somehow, a rocky world like Earth did form anyway. Suppose some unlikely combination of physics brought together the right materials in the right proportions and produced something small and solid and almost familiar, adrift in the dark between the stars. What would that world be like? Without a star, it would receive almost no external energy. No light. No consistent warmth radiating across millions of kilometers of space. The surface would be cold in a way that is difficult to fully picture, not the cold of a winter night or even the cold of Antarctica, but something far more complete and permanent. A cold that has no opposite, because the warmth that would balance it simply does not exist. A stable biosphere, the kind that supports trees and oceans and breathing creatures, requires energy flowing in continuously over billions of years. Life as we know it is not a brief event. It is a long, slow, patient process that leans entirely on a reliable source of light and heat arriving every single day without interruption. On a world with no sun, that process cannot begin. Complex ecosystems, land creatures, the whole layered web of life that took our own planet 4 billion years to develop, none of it has a foothold. None of it has anywhere to start. And yet the universe is under no obligation to be empty just because it is cold and dark. There are other possibilities, stranger ones, quieter ones, that we'll explore as we go further into this story. For now, let the image settle. A solar system that never assembled. A planet that perhaps formed anyway, wandering without orbit or warmth through a universe that is vast and old and mostly very, very dark. There is something strangely peaceful about that image, if you let yourself sit with it. The darkness is not empty. It is simply patient. There is a particular kind of darkness that is not about the absence of light, but about the absence of possibility. In a universe where the sun never formed, or where a rocky world somehow exists without one, life does not simply struggle. It faces a much more fundamental problem. It has almost nowhere to begin. On our own Earth, nearly every living thing traces its energy back to the same original source, sunlight. The grass, the insects that feed on it, the birds that feed on them, the whole elaborate structure of an ecosystem, all of it is, at its deepest root, converted starlight. Photosynthesis is the process that makes that conversion possible. Plants, algae, phytoplankton drifting in the upper ocean, they take light and carbon dioxide and water, and they produce food and oxygen. They have been doing this for roughly 3 billion years on our planet, and in doing so, they built the atmosphere that every breathing creature depends on. Without sunlight, that process never starts. And without photosynthesis, oxygen does not accumulate in the atmosphere. The air does not become breathable in any way we would recognize. The food webs that support animals, insects, birds, fish, they have no foundation to build on. Nearly every ecosystem we know, every food chain, every predator and prey relationship, begins with a plant or an alga capturing light. Remove the light, and the whole structure simply has no ground floor. This does not mean life is completely impossible in such a world. The universe is more creative than that. Deep beneath Earth's surface, geothermal heat rises from the planet's interior, energy left over from the original formation of the world and from the slow decay of radioactive elements in the rock. In our own oceans, hydrothermal vents pour hot, mineral-rich water into the cold deep sea, and around those vents, entire communities of organisms survive without ever seeing sunlight. Tube worms, shrimp, bacteria, life clustering around heat and chemistry rather than light. In a sunless world, that kind of life might be the only kind. Small, slow, dependent on whatever heat the planet itself can produce, confined to the warmest pockets near geothermal activity. It is not nothing. But it is a very long way from forests, and meadows, and the sound of birds in the morning. Complex surface life, the kind that walks and breathes and looks up at a sky, almost certainly could not emerge under those conditions. There is simply not enough energy flowing into the system. Life, in any form we would easily recognize, needs a generous and reliable energy source. A star, burning steadily across hundreds of millions of years, is one of the most reliable energy sources the universe produces. Without one, the surface of a world goes dark and cold. And the only life that persists, if any, does so quietly, in the deep places, where warmth still rises from the rock below. Now let's shift the thought experiment slightly. Instead of imagining a universe where the sun never formed, imagine something more immediate, more sudden. What if the sun, our sun, the one that rose this morning and will rise again tomorrow, simply vanished? Not dimmed, not gradually cooled, just gone. It's the kind of question that sounds alarming at first, but there's something strangely meditative about following it through slowly and carefully. Because what actually happens is not what most people would expect. For the first 8 minutes and 20 seconds, nothing changes at all. You would not know. No alarm would sound. No sudden darkness would fall across the sky. The sunlight arriving at Earth in those first minutes would be light that left the sun before it disappeared, light already traveling across space, already committed to its journey, already almost here. It would complete that journey regardless. For 8 minutes and 20 seconds, Earth would still be bathed in the last light of a star that no longer existed. This is one of those facts that, when you really sit with it, reveals something profound about the nature of light and distance. We do not see the sun as it is right now. We see it as it was 8 minutes ago. Every sunrise you have ever watched, every golden afternoon, every late light stretching across a wall, all of it was a message from the past, arriving slightly delayed, sent from a source you could never quite see in real time. And in those final 8 minutes of light, Earth would still be following its orbital path, curving around the point in space where the sun used to be, pulled by a gravitational force that, at the speed of light, had not yet communicated its own disappearance. Gravity, like light, is not instantaneous across cosmic distances. When the sun vanished, its gravitational influence would also cease, but that information would take the same 8 minutes and 20 seconds to reach us. So for those quiet final moments, Earth would continue its orbit, following a path around an absence, a ghost, a point in space that no longer held anything. Then the change would arrive. The last photons of sunlight would reach Earth's atmosphere. The sky, midday for half the planet, would go dark. Not gradually, suddenly. Stars would appear where blue sky had been moments before. The temperature would still be relatively normal, because the atmosphere holds heat for a while, but the source of that heat would be gone. And Earth would stop curving. Released from the sun's gravitational hold, it would continue moving, but in a straight line now, following the path it was on at the moment gravity disappeared, no longer being pulled into a gentle curve around a central body. It would travel outward into space, not falling, not orbiting, just going. There is something almost serene about that image, strangely enough. Meanwhile, deep underground and in research facilities around the world, something quiet and technical would also occur. Neutrino detectors, instruments designed to catch the nearly massless, almost undetectable particles that pour out of the sun's nuclear core by the trillions every second, would go silent. The sun produces an enormous stream of neutrinos constantly, and they arrive at Earth continuously, passing through everything, barely interacting with matter at all. They are one of the most invisible signals in physics. But they would stop. About 8 minutes after the sun's disappearance, the neutrino count would drop to almost nothing. For scientists monitoring those instruments, it would be the first hard confirmation that something fundamental had changed, not just a loss of light, but a loss of the nuclear processes that had been running for 4.5 billion years. The universe does not announce its changes loudly. Often, the biggest shifts arrive quietly, at the speed of light, in the form of something stopping rather than something starting. And in this case, what stops is everything we built our world around: warmth, light, orbit, and the long, patient energy that made complexity possible. What remains is a planet moving through the dark, carrying everything it once was, heading somewhere new with no particular destination in mind. There is a particular comfort in motion, in the feeling of going somewhere, even when you cannot see where that somewhere is. When the sun disappears from our thought experiment, Earth does not stop. It does not shudder or hesitate or collapse inward. It simply continues doing what it was already doing, moving. Physics is patient and consistent in that way. An object in motion stays in motion, and Earth has been in motion for 4.5 billion years. That momentum does not vanish just because the force that shaped it into a curve is no longer there. What changes is the shape of the journey. Where once Earth traced a gentle ellipse around its star, it now travels in a straight line, or close enough to one, through the complexity of space's geometry. A straight line outward, carrying everything with it. Every mountain and ocean and city and forest, moving together at roughly 108,000 kilometers per hour through the interstellar dark. That number is worth sitting with for a moment. 108,000 kilometers per hour. It sounds fast, and by any human standard, it is extraordinary. But space is so incomprehensibly large that even at that speed, Earth would take tens of thousands of years to reach even the nearest star system. The galaxy does not give up its distances easily. So Earth moves, carrying its passengers, its rocks, its frozen oceans, its dormant atmosphere, into a region of space it was never meant to visit. Not falling toward anything. Not orbiting anything. Just going. And as it goes, the sky begins to change. The first and most total change is the darkness. It arrives 8 minutes after the sun disappears, as we explored before, when the last light completes its journey and there is nothing following behind it. And then the sky, everywhere on the planet, becomes something humans have never collectively experienced before. True, permanent darkness. Not the darkness of a moonless night in the countryside, where your eyes adjust and eventually you can make out the shapes of trees and the pale silver of a path. Not the darkness of a power outage, where you know morning is coming. This is something different in kind. A darkness with no scheduled end, no source of relief on the horizon, no promise of a returning light. The familiar cycle of day and night disappears entirely. There are no more sunrises. There are no more sunsets, those long, golden, slow-fading moments that seem designed to ease you from one part of the day into another. The sky simply stays dark. The Earth still rotates, because rotation is its own kind of momentum and does not require a star. but the rotation no longer produces day and night. It just turns a dark side to face one region of space, and then turns it back. Every direction is night now. Look up, and you see stars. Distant, cold, beautiful, but so far away that their light, even combined, produces only a fraction of what our sun alone once offered on a typical afternoon. The stars are not nothing. They are ancient and real, and their light has traveled for years and centuries and sometimes millions of years to reach us. But they are not enough to read by. Not enough to grow food by. Not enough to warm a surface or drive weather or sustain the rhythms that life depends on. The sky becomes, in a strange way, more honest, more complete. Without the sun washing out everything else with its overwhelming brightness, the full depth of the universe becomes visible from any point on the surface. The Milky Way stretches overhead in full detail, not the faint suggestion of it that most people on Earth today can barely see through the light pollution of cities, but the real thing, dense and layered and ancient, a river of hundreds of billions of stars arching from one horizon to the other. It would be, in its own way, extraordinarily beautiful. But cold. And getting colder. Now, in the weeks and months before the freeze fully sets in, before we lose ourselves in temperatures, there is something else worth noticing in that dark sky. Something that most people probably never think about when they look up at night. The moon. The moon, in our current world, is one of the most reliable and comforting features of the night sky. It rises and sets on its own rhythm, cycling through its phases, sometimes a thin silver crescent low on the horizon, sometimes a full and luminous disk that casts shadows and lights up the night enough to walk by without a torch. Poets have written about it for thousands of years. Sailors have navigated by it. Wolves, in legend and sometimes in fact, raise their heads toward it. But here is the thing about the moon's light that is easy to forget: it is not the moon's own. The moon produces no light of its own. It is not a star. It has no internal energy source, no nuclear fusion, nothing burning or radiating from within. What we see when we look at the moon is sunlight, our sun's light, bouncing off the moon's dusty gray surface and traveling back toward us. The moon is, in the most literal sense, a mirror. A large, imperfect, cratered mirror, but a mirror nonetheless. Without the sun, the moon goes dark. Not immediately. For those first 8 minutes, everything still functions normally, the moon still gleams, the world still looks familiar. But once the sun's light is gone, the moon has nothing to reflect. It becomes invisible against the stars, a dark circle, a presence you might sense by the stars it blocks rather than by any light it produces. You could calculate where it was. You could track its position using instruments. But you could no longer simply look up and find it glowing there, the way generations of humans always have. The moon's phases, which have structured human calendars and agricultural cycles and spiritual practices across almost every culture in history, would no longer be visible. The cycle would technically continue, the moon would still orbit Earth, still move through its positions relative to where the sun used to be. But none of it could be seen. The whole visible drama of the lunar cycle would simply stop. This is one of those quiet losses that is easy to overlook when you're listing dramatic facts about planets going dark and temperatures plummeting. But the disappearance of the moon from the night sky represents the loss of something that has been part of human experience for as long as there have been humans. Longer than that, it has been part of every night active creature's experience for hundreds of millions of years. Animals that hunt by moonlight would lose their advantage. Tidal rhythms driven partly by the moon's gravity would continue. The moon's gravitational pull would still be there, but the visible, luminous, familiar presence overhead would be gone. And the night sky, for all its new honesty and depth, would be missing something that countless generations had never known a world without. The stars remain, of course. And in their own way, they are extraordinary, brilliant and numerous and impossibly varied in color and brightness if you look closely enough. But the light they provide is so diffuse, so scattered across the entire dome of the sky, that the surface below remains functionally dark. You would adapt, perhaps. Human eyes are capable of adjusting to low light over time. You might learn, after weeks in darkness, to navigate by starlight in a way that feels almost impossible to imagine right now. But it would be a different kind of seeing. A slower, more careful, more patient kind of seeing. The world would look like a very long exposure photograph, shapes visible, textures lost, color almost entirely absent, everything rendered in shades of dark gray and deep shadow. And all of this, the darkness, the loss of the moon's glow, the permanent starlit night, is just what happens to the sky. Below the sky, other changes are already underway. The temperature is beginning to fall. Not catastrophically yet. The atmosphere holds heat with more persistence than most people realize, but steadily, relentlessly, in one direction. The surface of a planet without a star is not given to warming back up on its own. The energy that drove weather systems, that evaporated water into clouds, that created the temperature differences between regions that cause wind, all of that is fading. The great heat engine of Earth's climate, which has been running continuously for billions of years, is winding down. What replaces it, for a while, is stillness. A profound, spreading, gradually deepening stillness, as the planet carries everything it ever was into a universe that did not arrange itself for its arrival. The stars are beautiful. The silence is immense. And somewhere in that dark, the world keeps moving at 108,000 kilometers per hour, carrying its quiet cargo through the long night between the stars. The planets, too, would vanish from the sky. It happens in the same way as the moon, and for the same reason. Mercury, Venus, Mars, Jupiter, Saturn, every planet visible to the naked eye from Earth's surface is visible for exactly one reason: it catches sunlight and throws some of it back toward us. They are not self-luminous. They do not burn. They are simply surfaces, some rocky, some wrapped in thick cloud, some banded with storms the size of continents, and all of them, without exception, lit from the outside. Take away the sun, and they disappear. One by one, or all at once, depending on where each one sits in its orbit and how the geometry falls. Within those first critical minutes after the light stops arriving, the familiar points of brightness that humans have tracked across the sky for thousands of years, the ones ancient astronomers named and mapped and told stories about, simply stop shining. They are still there, of course. Their mass remains. Their orbits continue. But to any eye looking up from Earth's darkened surface, they are indistinguishable from the black sky around them. The solar system, which was already a quieter place in our thought experiment, becomes quieter still. A collection of dark bodies moving through space with no star to illuminate them, no center to call home, just momentum and gravity and the long patience of physics. What is left visible in the sky is only what generates its own light, the distant stars, each one a sun in its own right, most of them too far away to provide meaningful warmth but close enough, some of them, to be genuinely beautiful. The sky becomes a map of every other solar system in the galaxy. Every point of light is a reminder that what Earth has lost is not unique. Stars are everywhere, burning steadily, warming their own planets, holding their own systems together. But ours is gone. And what follows, here on the surface, is a process as old and inevitable as thermodynamics itself. The climate begins to die. That phrase sounds dramatic, and perhaps it is. But it is also simply accurate. Earth's climate, every aspect of it, from the trade winds over the tropics to the monsoon seasons of South Asia to the gentle rain that falls on a forest in the afternoon, is powered by one thing: solar energy. The sun heats the surface unevenly, because of Earth's curvature and tilt and the different ways land and water absorb warmth. Those uneven temperatures create differences in air pressure. Those differences in pressure create wind. Wind moves moisture. Moisture rises, cools, condenses, and falls as rain. Rain fills rivers, rivers reach the sea evaporates under sunlight, and the whole cycle begins again. Every part of that cycle has the same root. Remove the root, and the whole system begins to unravel, not all at once, not in a single dramatic moment, but steadily, as the energy that kept it moving is no longer replenished. The water cycle is perhaps the most immediate casualty. Evaporation is driven almost entirely by solar heating. The sun warms the surface of the ocean, and water molecules gain enough energy to escape into the air as vapor. That vapor rises, cools at altitude, gathers into clouds, and eventually returns to the surface as precipitation. It is one of the most elegant and fundamental cycles on the planet, and it has been running continuously for billions of years. Without solar energy arriving at the surface, evaporation slows to almost nothing. The oceans stop feeding moisture into the atmosphere. Clouds stop forming over open water. The great rivers of moisture that flow through the atmosphere, invisible highways of water vapor that produce rainfall across entire continents, begin to thin and quiet. Rain becomes infrequent, then rare, then effectively absent. The atmosphere, deprived of its constant supply of solar-driven energy, begins to settle. Weather systems require temperature gradients, differences between warm and cool air masses, to sustain themselves. A warm front meeting a cold front produces a storm. A temperature difference between the equator and the poles drives circulation patterns that stretch across hemispheres. These gradients exist because the sun heats different parts of the planet differently, constantly, every single day. As the surface cools uniformly, those gradients collapse. There is no longer a warmer equator and colder poles in any meaningful sense. Everything is moving toward the same destination: cold. And as the temperature differences shrink, the winds that those differences produce begin to die down. Not immediately. The atmosphere carries its own momentum, and storm systems already in motion may continue for some time. But gradually, the great circulation patterns weaken. The jet streams slow. The trade winds fade. Winds that have blown in the same general direction for millions of years, shaping ocean currents and climate zones and the distribution of species across continents, simply ease. And then still. The silence that would follow is hard to fully imagine for anyone who has grown up with weather as a constant backdrop of life. Wind is so universal, so ordinary, such a basic feature of being outside on any given day, that its absence would feel profoundly strange. A world where the air does not move, where leaves do not rustle, where the surface of water is not riffled by even a light breeze, where the flags hang completely motionless because there is simply nothing to move them. But before that silence fully settles, there is the matter of temperature. And this is where the scale of what is happening becomes most tangible. Earth's atmosphere is often described, in this context, as a blanket. And that is a useful image, because it captures something real. The atmosphere does retain heat. It traps some of the warmth that the surface has absorbed over billions of years of solar heating, slowing the rate at which that heat radiates back out into space. Without an atmosphere, if Earth were a bare rock like the Moon, the temperature would plunge almost instantly to the deep cold of outer space. Somewhere around -270 degrees Celsius at night, with wild swings between sunlit and shadowed sides. Earth's atmosphere buffers all of that. It is genuinely protective, genuinely insulating, genuinely capable of holding on to warmth for longer than a bare surface could manage. So the cooling, when it comes, is not instantaneous. It does not happen in minutes or hours. But it happens within days. Within roughly a week, some estimates suggest as few as 7 to 10 days, average surface temperatures in many regions of the planet would fall below freezing. This is not a gentle transition. A week is an almost absurdly short amount of time on any geological scale. A week is nothing. And yet that is approximately how long it takes for the absence of solar input to overcome the atmosphere's insulating capacity and push temperatures past the point where water freezes. Freezing is significant not just as a comfort issue but as a physical threshold. When water freezes, it changes the behavior of everything it is part of. Rivers slow and then stop. Lakes develop ice at their surfaces. Soil hardens. The moisture that was still present in the air begins to fall not as rain but as snow, and then, as temperatures continue to drop, snowfall itself becomes less frequent, because the atmosphere grows too cold and dry to carry much moisture at all. The surface of the world begins to lock. Not all at once, different regions cool at different rates depending on altitude and proximity to large bodies of water, which hold heat longer than land does. Coastal areas might stay marginally warmer for longer. The deep oceans, with their enormous thermal mass, would resist freezing for a very long time, years, perhaps decades, depending on how far down you look. But the surface, the thin, familiar, livable surface where soil meets air and where every terrestrial ecosystem exists, would be moving rapidly toward a state that nothing alive there is built to survive for long. The cold is patient. It does not rush. It simply continues, degree by degree, in the same direction, with no solar warmth arriving to push back against it. And in the darkness and the growing stillness, Earth carries on its journey through space, the temperature dropping behind it like a wake, the last warmth of a 4.5 billion year relationship with a star slowly, irreversibly, dispersing into the void. There is something almost meditative about the scale of it. The slowness of some parts, the swiftness of others. The way something as total as the death of a planet's climate does not announce itself with a single catastrophic event, but instead arrives as a gradual series of familiar things becoming quieter, less wind, less rain, less warmth, less movement, until the world that was is replaced by something still and cold and dark and, in its own way, complete. The stars are still there. They always are. Steady and indifferent and impossibly beautiful, scattered across the permanent night above a world that is growing quieter with every passing day. 20 degrees Celsius per day. That is the estimate some scientists give for the initial rate of cooling once the sun is gone. Not the eventual average, not the long-term steady state, but the rate at which the surface temperature falls in those first critical days, the period before ice begins to form and before the various systems that slow the cooling have had time to take effect. 20 degrees per day is a number that becomes more striking the longer you sit with it. On an ordinary Earth, a temperature swing of 20 degrees over the course of a season is enough to change the landscape entirely, from summer to winter, from green to white, from birdsong to frost. A swing of that magnitude in a single day, repeated day after day with nothing to reverse it, is something outside the range of anything life on this planet has experienced in its entire history. The first day, perhaps, feels like an unusually cold autumn. The second, a hard winter. By the end of the first week, temperatures in temperate regions have reached depths that only the poles normally see. By the second week, even those comparisons begin to fail. There is no familiar season left to reach for. And as the temperature falls, the water begins to change. Water is one of the most remarkable substances in the known universe. It behaves in ways that seem almost deliberately arranged to support life, expanding when it freezes rather than contracting, which means ice floats rather than sinks. It holds heat with unusual persistence. It exists as liquid across a wide range of temperatures. It is, in almost every meaningful sense, the substance that made complex life on Earth possible. And now, in this darkened world, it begins to freeze. The smallest bodies of water go first. Small ponds, the kind you might find at the edge of a field or in a quiet corner of a park, have relatively little thermal mass. They cannot hold heat for long against a sustained drop in air temperature. Within days of the sun's disappearance, these small, still, shallow bodies of water would begin to freeze solid. Not just a thin crust at the surface, but all the way through, the cold reaching down to the bottom and leaving behind something that looks, from a distance, like cloudy glass set into the earth. Streams slow. Rivers, especially smaller ones in higher altitudes, begin to thicken at their edges, ice forming along the banks first and then creeping inward toward the current. The current itself resists. Moving water freezes more slowly than still water, but the cold is relentless and the current is losing the solar-driven temperature gradients that kept it moving briskly. Eventually, rivers that have flowed continuously for millions of years grow quiet, and then still, and then solid. The oceans are a different matter entirely. The oceans are vast in a way that is genuinely difficult to convey. They cover more than 70% of Earth's surface and extend, at their deepest points, nearly 11 kilometers down. The total volume of water in Earth's oceans is roughly 1.335 billion cubic kilometers. All of that water has absorbed solar energy over billions of years, and all of that stored heat does not simply vanish when the source of new energy is removed. The ocean is, in this sense, a thermal battery of staggering capacity. It resists the cold far longer than the land, far longer than the atmosphere, far longer than anything else on the surface. But the ocean surface, exposed directly to the freezing air, begins to lose heat relatively quickly. Within weeks, not instantly, but within weeks, the surface layers of the ocean begin to cool to the point of freezing. Ice begins to form. And here, the extraordinary physics of water reveals itself again. Ice floats. This seems like a simple fact, almost too basic to comment on. But in the context of a freezing world, it is everything. When ice forms on the ocean surface, it does not sink to the bottom. It stays at the top, and in doing so, it acts as an insulator. It creates a barrier between the freezing air above and the still liquid water below, slowing the transfer of heat from the ocean to the atmosphere. The ice itself is a kind of protection, not for the organisms trying to survive at the surface, but for the vast, dark, liquid world beneath. Under the growing ice sheet, the deep ocean remains liquid. Not warm by any human standard, the deep ocean is cold even in the best of times, hovering just a few degrees above freezing under normal conditions. But liquid. And in that cold, pressurized, lightless deep water, the conditions for a certain kind of life persist for far longer than anyone standing on the frozen surface might imagine. The ocean freezes from the top down, and the top is only the beginning. The process plays out over months, and then years. The ice sheet thickens. It spreads. From the poles, where freezing begins earliest because those regions were already coldest, ice advances toward the equator. The Arctic and Antarctic ice caps, which in our own time have been receding due to warming, now grow with a speed and purpose they have not shown in millions of years. They advance across latitudes, across what were once temperate seas, across the warm blue waters of the tropics. The equator is the last to freeze. It started warmest. All those billions of years of direct overhead sunlight had given the tropical regions the largest thermal reservoir, and so it holds out longest. For a while, there may be open water at the equator while the rest of the world's oceans are already locked under ice. A narrow belt of liquid sea, shrinking week by week, the last remnant of the world's open water, circling a dark and frozen planet. And then it, too, closes over. And the oceans are ice, surface to horizon, in every direction. Beneath that ice, in the pressurized dark, the deep ocean may remain liquid for a remarkably long time, years, perhaps decades, possibly longer. The geothermal heat rising from Earth's interior, the same heat that would sustain any life in a sunless world, continues to warm the deep water slightly, preventing complete solidification near the ocean floor. Hydrothermal vents continue to pour hot water into the dark. The chemistry of the deep sea continues, slowly, in a world that above the ice would be almost unrecognizable. Life in those depths, if it persists, if it is hardy enough, would not know that anything had changed. The deep ocean is already lightless. It is already cold. It is already pressurized and alien by surface standards. For the organisms that evolved to live there, the disappearance of the sun is, at first, almost irrelevant. They never saw it. They never needed it. They have been living off geothermal chemistry for millions of years, and they will continue to do so, patient and invisible, under a ceiling of ice kilometers thick. It is one of the stranger comforts in this whole imagining, the idea that somewhere, in the deep dark beneath the frozen ocean of a sunless world, life continues. Quietly. Without drama. Doing what it has always done, entirely unaware of the catastrophe unfolding above. On the surface, meanwhile, the temperature continues its descent. This is no longer a process measured in the degrees of familiar seasons. The comparison that scientists reach for, at this stage of the timeline, is Mars in winter. Mars, that cold, red, thin-atmosphered world, experiences winter temperatures near its poles of around -100 degrees Fahrenheit. Roughly -70 or 73 degrees Celsius, depending on the location and the year. It is a temperature at which carbon dioxide, the main component of Mars's thin atmosphere, actually freezes and falls to the ground as dry ice. Earth, in this scenario, moves toward those temperatures. Not immediately, the ocean ice in the remaining atmosphere provides some insulation, slowing the final plunge. But the direction is clear and the destination is cold in a way that makes Mars in winter feel almost like a benchmark to reach, rather than an extreme to avoid. At -100 degrees Fahrenheit, the world is not merely cold. It is a fundamentally different physical environment. Materials that are flexible and workable at room temperature become brittle. Liquids that we take for granted freeze into solids. Air itself, not just water vapor, but the gases that make up the atmosphere, begins to behave differently, some components becoming denser and sinking, others thinning further as the cold strips energy from every molecular interaction. The atmosphere itself, over long enough timescales, may begin to freeze. Nitrogen, the main component of Earth's air, liquefies at around -196 degrees Celsius. Carbon dioxide freezes at -78 degrees. If temperatures continue dropping without limit, and in a sunless world, there is no obvious reason they would stop. The atmosphere might eventually begin to condense and fall, literally snowing out of the sky in components, leaving the surface increasingly bare and the pressure dropping toward the near vacuum of open space. But that is a long way off. In the time frame of weeks and months, what the surface looks like is simply a world of ice and silence and a sky full of stars that have never seemed so close or so cold. There is something in all of this that is worth acknowledging, not with fear, but with a kind of quiet wonder. The earth that we know, warm, wet, loud with weather and life and the sound of wind, is not a permanent condition. It is a relationship. A long and extraordinarily fortunate relationship between a planet and a star, sustained across billions of years, producing as its result everything that has ever lived or thought or looked up at the sky in curiosity. That relationship is easy to take for granted, because it has always been there. Every human who has ever existed was born into it. Every sunrise was part of it. Every warm afternoon, every summer, every growing season, all of it is the product of a star burning steadily at the center of the solar system, day after day, for longer than the mind can comfortably hold. The thought experiment of its absence is not a cause for fear. It is an invitation to see the ordinary for what it is, something extraordinary, sustained and generous and almost incomprehensibly ancient, arriving every morning without fail and asking nothing in return. The ice spreads in the dark. The deep ocean holds its warmth. The stars look on, steady and indifferent, across the frozen silence of a world that is going somewhere new. By the end of the first year, the numbers have moved beyond anything that maps to ordinary human experience of cold. -100 degrees Fahrenheit. That is the estimate some models suggest for Earth's average surface temperature within roughly 12 months of losing the sun average, meaning that some places would be colder still, and a few, through the strange persistence of geothermal warmth or the insulating depth of remaining ice, might be marginally less so. But as a global average, it represents a planet that has crossed a threshold from which no natural recovery is possible. There is no season on the other side of this. There is no spring coming. The atmosphere still exists, still clings to the surface, still provides a thin buffer against the absolute cold of open space. But it is quieter now. Thinner in its behavior if not yet in its composition, the weather systems that once churned through it having faded to almost nothing. The air is still. The sky is dark. The stars are brilliant and unchanging overhead. And on the surface of this world, something that has been underway since the first day of darkness is reaching its full and devastating conclusion. Life is collapsing. It does not happen the way catastrophes are sometimes imagined, not in a single dramatic moment, not with a clear before and after. It happens in stages, each one following from the last with a kind of terrible logic, each loss creating the conditions for the next. It begins at the base of everything and works its way upward, dismantling in months what took billions of years to build. The base is photosynthesis. And photosynthesis stops on the first day. The moment sunlight ceases to arrive at Earth's surface, every photosynthesizing organism on the planet loses its energy source. Plants, algae, phytoplankton drifting in the sunlit upper layers of the ocean, all of them are built around the same fundamental process, the capture of light energy and its conversion into chemical energy stored as sugar. That process requires light in the way that a fire requires fuel. Remove the light, and the process stops. Not gradually, not reluctantly, but immediately and completely. There is no stored sunlight. There is no reserve of incoming photons to draw on. The moment darkness is permanent, photosynthesis is over. what follows from that single fact is a cascade that touches everything. But here is something worth pausing on, because it is one of those details that surprises almost everyone who encounters it for the first time. The end of photosynthesis does not mean the immediate end of breathable air. Oxygen, the product of billions of years of photosynthetic activity, has accumulated in Earth's atmosphere to a concentration of roughly 21%. That is an enormous reservoir, not a flow, but a stock. A vast quantity of gas already present in the air, built up over geological timescales, not replenished moment to moment like sunlight but simply there, present, available. Stopping photosynthesis cuts off the production of new oxygen. But it does not drain the existing supply. The oxygen already in the atmosphere could remain at breathable levels for thousands of years. Some estimates suggest tens of thousands of years, depending on how much biological activity continues to consume it. In a world where most life has died, oxygen consumption drops dramatically. The atmosphere, cold and still and dark, might hold on to its oxygen content for an extraordinarily long time, long after the surface is frozen, long after the ecosystems have collapsed, long after any creature capable of breathing it is gone. There is something almost melancholy about that. An atmosphere still technically breathable, still chemically capable of sustaining life, surrounding a world where there is nothing left alive to breathe it. But that is the end of the story. In the first days and weeks, the collapse is just beginning, and it starts with the plants. Most plants are not built for darkness. They are built for light, their entire architecture, from the broad flat surface of a leaf designed to catch sunlight to the chemical machinery inside each cell, is oriented toward capturing and using solar energy. Without it, they cannot produce food. Their sugar reserves, the chemical energy stored in roots and stems and seeds, can sustain them for a short time. But those reserves are limited, and without photosynthesis to replenish them, they run down. Grasses die quickly. Annual plants, those that complete their life cycle within a single growing season and depend entirely on current photosynthetic activity, begin to fail within days. The green drains from the world's fields and meadows, not from frost alone, though the frost accelerates everything, but from a more fundamental starvation. The machinery of life runs out of fuel. But the large trees are different. And this is one of the genuinely surprising details in the story of a sunless Earth. A large, old tree is not just a photosynthesizing machine. It is also a storage system, a living warehouse of accumulated energy in the form of sugars, starches, and other organic compounds distributed through its wood, its roots, its bark. A tree that has been growing for decades or centuries has built up reserves that are, by the standards of most plants, enormous. Its metabolic rate is slower. Its internal processes tick along at a more measured pace. It is not consuming its reserves as quickly as a small annual plant would. Large trees could survive for years without sunlight. Some estimates suggest decades, drawing on stored energy, maintaining minimal metabolic function, alive in a technical sense even as the world around them dies. A great oak or a redwood or an ancient baobab, standing in the dark and the cold, leafless of course, its photosynthetic activity long since halted, but still technically living, still conducting the slow chemistry of survival in its heartwood, for years after the last grass has died and the last annual plant has given up. It is a strange image. A forest of bare, dark trees, massive and silent and somehow still holding on, surrounded by a frozen world, their stored energy ticking down year by year toward an inevitable end. But they would fall eventually. The cold would reach them. Their stored energy would run out. And one by one, or perhaps all together as some particularly brutal temperature threshold is crossed, even the trees would go. The animal world watches all of this happen, and responds with a logic that is ruthless and immediate. Herbivores, the animals whose diet consists of plants, grasses, leaves, fruits, seeds, find their food source disappearing almost immediately. The grasses go first. The smaller plants follow. The animals that depend on them face starvation not as a distant possibility but as a present reality, beginning within days or weeks of the sun's disappearance. Deer, cattle, elephants, rabbits, horses, the vast majority of the world's large mammals, all of them are, at some level, dependent on plant life. They begin to die. The carnivores last longer. A predator does not depend directly on plants. It depends on the animals that depend on plants, and so there is a time delay built into its vulnerability. While the herbivores are still alive and weakening, there is food for carnivores. Lions, wolves, eagles, they feed on what is available. For a time, perhaps, they feed more easily than they ever did, because weakened prey is easier prey. But it is a resource that is being consumed without being renewed, and every herbivore that dies brings the predator one step closer to the same fate. The food chain is not a ladder you can survive on if the lower rungs are removed. It is more like a structure where every level depends on the one below it. When the base collapses, everything above it eventually follows, however long it takes, however many steps removed. And then there are the scavengers. Scavengers occupy a remarkable ecological position under normal circumstances. They are the cleanup crew, the recyclers, the organisms that extract value from death and return nutrients to the soil. Vultures, hyenas, ravens, various beetles and flies and bacteria. In a healthy ecosystem, they are essential but often overlooked. In a dying one, they are, for a time, the most successful animals alive. As the herbivores die and the predators follow, the scavengers find themselves surrounded by more food than they have ever had access to before. The cold actually helps them in one macabre sense. At very low temperatures, decay slows dramatically, meaning that dead animals remain available as food for much longer than they would in a warm environment. A frozen carcass is a resource that lasts. For weeks, possibly months, scavengers could persist on this frozen abundance. Moving across an icy, dark landscape, feeding on the remains of ecosystems they were never built to outlast. They are the last large animals in many regions, the final chapter of a surface ecology that once included millions of species interacting in extraordinary complexity. But the cold is comprehensive. It does not make exceptions for adaptability or cleverness or ecological flexibility. The temperature keeps falling, the food keeps running out, and even the scavengers reach a point where the environment is simply beyond what any surface-dwelling creature can endure. What remains, after all of this, is quieter than almost anything that has existed on Earth's surface since the first life appeared 3.5 billion years ago. The ice is total. The air is still. The darkness is complete above the frozen surface. And somewhere below, in the deep ocean under kilometers of ice, in the cracks of rock where geothermal heat still rises, in the stubborn chemistry of hydrothermal vents, the simplest life continues. Bacteria, archaea, the ancient lineages that were old before complex life existed, before the dinosaurs, before the first fish, before the first cell with a nucleus. They have survived every mass extinction in Earth's history. They survived the asteroid that killed the dinosaurs. They survived the great oxidation event that poisoned the early atmosphere. They are, in many ways, the true survivors, the organisms that define the lower limit of what life requires to persist. In the deep, cold, pressurized dark beneath the ice, they continue their slow and ancient chemistry. Indifferent to the catastrophe above. Unaware of the star that is gone. Doing what they have always done, as they have always done it, for as long as life has existed on this planet. It is, in a strange and quiet way, a form of hope. Not hope for the world we know, that world is gone, or going, irretrievably. But hope in the sense that life, once it takes hold in a universe, is not easily removed. It finds the margins. It persists in the deep places. It carries on in the cold and the dark, patient and small and enduring. The surface of Earth, a year into its journey without a sun, is a place of extraordinary stillness. The ice stretches from horizon to horizon in every direction. The atmosphere is thin and cold and silent. The stars above are brilliant and steady, the same stars that look down on oceans and forests and cities and living creatures, now looking down on ice. The planet is still moving. 108,000 kilometers per hour through the interstellar dark, carrying its frozen cargo, its hidden deep ocean life, its atmosphere of breathable air that no one is breathing, moving through a universe that is vast and old and largely cold, toward no particular destination, with no particular purpose. Just going. Just continuing. The way things do when they have momentum and nowhere specific to be. There is a kind of peace in that, if you let yourself find it. The world is different. The world is, by every human measure, gone. But it is still there, still a planet, still moving, still carrying the chemistry of life in its depths, still turning gently in the dark. The stars are patient. The cold is thorough. And somewhere beneath the ice, in the oldest and simplest expressions of life that this planet ever produced, something is still, quietly, alive. There is a rhythm to being alive that most creatures never consciously notice. It runs underneath everything, the timing of sleep and waking, the cycle of hunger and rest, the seasonal pull toward migration or hibernation or reproduction. In animals, including humans, this rhythm is biological in the most literal sense. It is written into the chemistry of cells, regulated by hormones, adjusted continuously by one primary signal from the outside world. Light. The sun does not only provide warmth and energy for photosynthesis, it also provides time. The daily cycle of light and darkness is the clock that almost every living thing on Earth has used to organize its internal processes for hundreds of millions of years. Animals wake at dawn not simply out of habit but because the light itself triggers hormonal responses, cortisol rising, melatonin fading, the body shifting from its nighttime state into its daytime one. The cycle of a day is written into biology as surely as any genetic code. Without sunlight, that clock loses its signal. The disruption would be immediate and profound. Animals that depend on light cues to regulate feeding, sleeping, mating, and migration would find their internal systems drifting, no longer anchored to a reliable external rhythm, their biological clocks running on their own momentum, gradually losing coherence with one another and with the world outside. Migratory birds, which use the changing length of days to time their journeys across continents, would have no seasonal signal to respond to. Nocturnal animals, whose entire behavioral architecture is organized around the transition from day to night, would find that transition simply absent. Humans, too, would feel this loss in a way that goes beyond the obvious discomfort of darkness. Vitamin D, which the human body produces in the skin in response to ultraviolet light from the sun, would no longer be synthesized. UV light, the same radiation that causes sunburn in high doses, is also essential to a chemical process in the skin that converts a precursor molecule into one of the most important vitamins in human biology. Without it, vitamin D production stops. Dietary sources exist, and in the early period of a sunless world, human populations with access to food supplies might compensate for a time. But over weeks and months, the deficiency would compound, weakening bones, impairing immune function, affecting mood and neurological health in ways that would add one more layer of difficulty to an already impossible situation. The sun is not merely an energy source. It is woven into the biology of life on Earth in ways that took billions of years to develop, in ways that assume its presence so completely that its absence creates problems in places you would not immediately think to look. And then there is the matter of the fuels we have built civilization on. Coal, oil, natural gas, the fossil fuels that powered the Industrial Revolution and that still, in the early decades of the 21st century, provide the majority of the world's energy, are, at their most fundamental level, stored sunlight. They are the compressed, transformed remains of ancient organisms, plants and algae and marine life that captured solar energy through photosynthesis hundreds of millions of years ago, died, were buried, and under enormous heat and pressure were converted over geological timescales into energy-dense carbon compounds. Every time a coal plant burns coal to generate electricity, it is releasing energy that originally arrived from the sun during the Carboniferous period, 300 million years ago. Every barrel of oil is, in this sense, a message from an ancient summer, energy that fell on a warm prehistoric sea and was captured by microscopic life and stored in the rock for longer than the dinosaurs existed. Without sunlight, that process stops. No new photosynthesis means no new organic material being captured and buried. The reserves that exist are finite, already being depleted, and nothing is being added to them. In a human timescale, This might seem irrelevant, since fossil fuel reserves were already expected to run low within centuries even under normal conditions. But in the context of a sunless world, it underscores something important. Almost every form of concentrated energy that life and civilization depend on traces back, ultimately, to a star. Geothermal energy does not. Nuclear energy, in the sense of fission from radioactive elements present in Earth's crust, does not. These are forms of energy that exist independently of the Sun, drawing on heat from the planet's formation and from the decay of heavy elements seeded into the solar nebula by ancient stellar explosions long before our Sun existed. They are, in a sunless world, among the very few energy sources that remain. And it is around these sources that the last refuges of life take shape. The surface is dying. In fact, for most practical purposes, surface life is already gone or going. The cold has been comprehensive, the food chains have collapsed, the ecosystems that once covered every continent with extraordinary complexity have been reduced to frozen silence. But the planet is not uniformly dead. Not yet. Not if you know where to look. Go deep enough into the ocean, and the world changes. Below the ice that now covers the ocean surface, below the dark and increasingly cold upper water layers, the deep ocean persists in conditions that are, by its standards, almost normal. It was always cold down there. It was always dark. The pressure at the deepest points is extraordinary, more than 1,000 times the atmospheric pressure at the surface, and the temperature hovers just above freezing even under the most favorable circumstances. For creatures adapted to those conditions, the disappearance of the sun has not yet fundamentally changed their world. The ice above them is a ceiling, not a death sentence. It insulates the water beneath from the worst of the cold above. The thermal mass of the deep ocean, all those billions of cubic kilometers of water, resists cooling with enormous persistence. While the surface froze within weeks, the deep ocean will take far, far longer to reach temperatures that threaten the life within it. We are talking about timescales that dwarf anything in human history. Years. Decades. Possibly much longer. And in the deep ocean, there are places where the cold is actively pushed back. Hydrothermal vents are among the most extraordinary environments on Earth. They occur where the ocean floor is thin or fractured, where the geological activity of the planet brings magma close to the surface, where seawater seeps down into hot rock and is driven back up, superheated and mineral-rich, through chimneys of precipitated metal sulfides that can reach several stories tall. The water that emerges from these vents can be extraordinarily hot, in some cases, hundreds of degrees Celsius, kept liquid only by the immense pressure of the water above. Around these vents, entire ecosystems exist in complete independence from the sun. Chemosynthetic bacteria use the chemical energy in the vent fluid, hydrogen sulfide and other compounds, the way surface plants use sunlight. They are the base of a food web that includes tube worms several meters long, ghostly pale shrimp, crabs, fish, and a host of other organisms that have never needed and never used solar energy at any point in their evolutionary history. These ecosystems are powered by the Earth itself, by the heat of the planet's interior, by the radioactive decay of elements that were present in the rock long before the first cell ever existed. They are, In a profound sense, the original life support system, older than photosynthesis, independent of it, capable of persisting regardless of what happens at the surface. In a sunless world, these vent communities become the most fortunate ecosystems on the planet. While everything above them is dying, they continue. The chemistry of the vents does not change because the sun is gone. The heat keeps rising. The minerals keep flowing. The bacteria keep feeding. The tube worms keep growing. The shrimp keep grazing. Time passes. The ice thickens above. The surface world becomes a frozen, airless memory. And in the deep ocean, around the vents, life carries on, small, strange, unhurried, sustained by the interior of the planet rather than by its star. Go deeper still, into the rock itself, and you find another refuge, stranger and more ancient even than the vent communities. Within Earth's crust, kilometers below the surface, microorganisms live in the pores and fractures of rock, in thin films of water that persist at temperatures and pressures and chemical conditions that would destroy most surface life instantly. These are some of the most extreme organisms known to science, bacteria and archaea that reproduce so slowly their generation time can be measured in thousands of years, that derive energy from the chemical reactions between rock and water, that have likely been living in these conditions for millions or hundreds of millions of years without any significant contact with the surface world above. They do not know about photosynthesis. They do not know about ecosystems. They do not know about extinction events or climate collapse or the disappearance of a star. They know only the slow chemistry of rock and water and the gradual release of energy from mineral reactions, and that is enough. It has always been enough. In a sunless world, these deep crustal microorganisms are the most insulated life on the planet. The temperature changes happening at the surface, catastrophic by surface standards, barely register kilometers below. The cold that is freezing the oceans and killing the forests is a surface phenomenon, and the deep crust is not the surface. The geothermal heat that rises from the mantle continues to warm the rock around these organisms. Their world, their slow and ancient and simple world, continues with almost no interruption. This is, perhaps, the most important thing to understand about life in the context of this thought experiment. Life on Earth's surface, the life we see, the life we are part of, the extraordinary complexity of ecosystems and species and behaviors and relationships, is a relatively recent and specialized expression of something much more fundamental and much more durable. The deep microbial world is older than complex life. It is simpler. It is slower. And it is, in the most literal sense, more deeply embedded in the planet itself. The surface world required a star. The deep world requires only the planet. And the planet, in this scenario, still exists. Still carries its internal heat. Still drives its geothermal processes. Still hosts, kilometers below the frozen surface, the slow chemical reactions that have sustained microbial life since long before there were any plants or animals to look at. Over an enormously long time frame, longer than human civilization, longer than the existence of complex life, longer than most things we have frameworks for, Earth in a sunless scenario would eventually reach what scientists call a cold equilibrium. a state in which the loss of heat to space is balanced by the internal heat production of the planet itself. A very cold state, far colder than anything on the surface today, but a stable one. Not getting colder indefinitely, but arriving at a temperature determined entirely by what the Earth can produce from within. In that equilibrium, the surface would be a frozen, airless, dark and silent place. But the deep interior would still be warm. The hydrothermal vents, if they still existed in some form, would still be flowing. The deep rock would still be hosting its ancient microbial communities, reproducing slowly, metabolizing slowly, utterly patient and utterly indifferent to the cosmic event that ended the world above them. Life, in this scenario, does not end. Not completely. Not quickly. It retreats. It simplifies. It descends into the deep places where the planet's own heat is enough to sustain it. And it waits, though waiting implies an expectation of change, and these organisms have no such expectation. They simply persist. As they have always persisted. As they will continue to persist, for as long as the planet holds its heat and the chemistry remains possible. There is something genuinely moving about that, if you let yourself feel it. Not moving in a dramatic way, not the movement of a story with heroes in struggle and resolution, but moving in the quiet way that very old and very patient things can be moving. The way a mountain is moving if you really think about what it is and how long it has been there. Life found a way onto this planet more than 3.5 billion years ago. It has survived everything since. Asteroid impacts. Volcanic winters. Oxygen crises. Snowball glaciations. Mass extinctions that wiped out the majority of species alive at the time. Every catastrophe, every change, every transformation, something survived. Something always found the margin, found the deep place, found the chemical reaction that was still possible when everything else had stopped. The loss of the sun would be, by any measure, the most total catastrophe Earth's life has ever faced. And even then, in the deepest, oldest, most fundamental expressions of what life on this planet is, something would persist. The stars look down on a frozen world drifting through the dark. Beneath the ice, the old chemistry continues. The planet turns slowly, still holding its warmth in the deep rock, still providing the minimum conditions for the minimum forms of life. It is enough. For now, it is enough. And in the dark and the cold and the silence, that small, stubborn enough is quietly extraordinary. For as long as human beings have existed, survival has meant adapting to the environment around them. Shelter from wind and cold. Fire to extend warmth beyond what the sun provided. Agriculture to multiply the energy captured from sunlight into food. Every technology, every innovation, every structure humans have ever built has been, at some level, a way of living more comfortably within a world defined by a star. Even the most sophisticated modern city, with its steel and glass and climate-controlled interiors, is ultimately a refinement of the same basic project, taking what the sun provides and making it more reliable, more accessible, more evenly distributed among the people who need it. In a world without the sun, that project does not simply become more difficult. It changes in kind. Open-air civilization ends. There is no version of a sunless Earth where people continue to farm fields and move between cities and live in houses with windows. The cold, the darkness, and the collapse of every natural food system make the surface uninhabitable within months. Whatever human survival looks like beyond that point, it does not look like anything from the previous 100,000 years of human history. It looks like something new, something engineered, something deliberate, something requiring a level of technological and organizational sophistication that pushes right up against the limits of what humanity could realistically achieve under the most extreme pressure imaginable. Underground. That is where survival goes. Not underground in the metaphorical sense of hiding or retreating, but literally underground, beneath the surface, beneath the cold, in spaces carved out of rock or built into existing cave systems, insulated from the temperature that is killing everything above. Bunkers, in the broadest sense. Sealed habitats with their own atmospheres, their own food production systems, their own water cycles, their own sources of heat and light and power. The power question is the central one. Everything else follows from it. Because underground, cut off from sunlight, cut off from wind, cut off from every renewable energy source that depends on the star, the only viable long-term power sources are the ones that do not require the sun at all. Geothermal energy is the most immediately available. The heat rising from Earth's interior does not care that the sun is gone. It rises regardless, from the slow decay of radioactive elements deep in the mantle and from the residual heat of the planet's formation. In volcanic regions, in areas of high geothermal activity, this heat is accessible close to the surface, already used in places like Iceland to heat homes and generate electricity. In a sunless world, those geothermal resources would become among the most valuable things on the planet. The communities nearest to them, with the engineering capability to harvest them, would have the best chance of extending human survival indefinitely, or at least for much longer than anyone living on the frozen surface. Nuclear energy offers another path. Fission reactors, powered by uranium or thorium, generate heat through nuclear reactions that are entirely independent of sunlight. A well-designed reactor, with sufficient fuel and maintenance capacity, can generate reliable power for decades. In a sealed underground habitat, a nuclear reactor provides heat, electricity for lighting and air circulation, power for hydroponic growing systems that could produce food in artificial light. It is not comfortable, by any standard we would recognize today. But it is, technically, survivable. Food production underground would almost certainly mean hydroponics, growing plants in artificial light, in nutrient-rich water solutions, in carefully controlled environments. It is a technology that already exists and already works, used in vertical farms and research stations around the world. Scaled up, powered by nuclear or geothermal energy, it could sustain a human population. A small one. A carefully managed one, where every calorie is accounted for and every system is maintained with meticulous care, because there is no margin for failure when the alternative to a functioning food system is a frozen surface where nothing grows. The psychological dimensions of such an existence are worth acknowledging, because they are real and they are enormous. Human beings evolved in open air and open landscape. We are built for space, for horizon, for the change of seasons and the passage of light through the day. An existence entirely underground, under artificial light, with no sky and no weather and no outdoor world to step into, it is a kind of existence that has no real precedent in human history. Even the most isolated communities, even the most extreme environments humans have ever inhabited, have had the sky above them and the ground open to them. Underground survival would require not just technological innovation but a profound psychological and cultural adaptation. New rhythms of life. New definitions of normalcy. New relationships with darkness and enclosure in the absence of the natural world that shaped human consciousness over hundreds of thousands of years. Whether it could be sustained across generations, whether children born underground, who had never seen a sky or felt a breeze, could build lives and communities and cultures that remain coherent over centuries, is genuinely unknown. It is possible. Human adaptability is remarkable, and the impulse to persist, to build, to find meaning even in the most constrained circumstances, seems to be among the most fundamental human traits. But it would be survival in the most stripped-down, provisional sense of the word. Not a civilization in any form we would currently recognize. Something smaller. Something harder. Something that preserved, perhaps, the biological fact of humanity while losing most of what has historically made humanity what it is. And even then, even in the best-case scenario of underground habitats and nuclear power and carefully maintained food systems, the long-term prognosis for human survival on a sunless Earth is not optimistic. The planet itself becomes less hospitable over timescales of years and decades. The cold deepens. The atmosphere, though it holds its oxygen for thousands of years, begins to change in composition and behavior. The surface resources that underground communities would initially depend on, materials, minerals, water accessible near the surface, become harder to reach as temperatures fall and ice thickens, and the equipment needed to access them requires more and more energy to operate in the cold. Earth would not remain habitable in the long term. Not for humans. Not for anything complex. The deep microbial life would persist, but the window for anything larger than a microorganism is measured in centuries at most, likely far less for anything requiring the organizational complexity of human civilization. The last refuge is temporary. The survival is provisional. But the fact that it is possible at all, that human ingenuity, applied urgently to the right problems, could extend the story even by decades or centuries, is not nothing. It is, in its own way, a testament to what intelligence can accomplish even at the very edge of what a planet can offer. And then the conversation shifts, from what happens on the surface of a sunless world to what happens above it. Because the sun's disappearance does not only change Earth. It changes the entire space environment that Earth moves through. There is a structure in space called the heliosphere. It is enormous, so enormous that even with the fastest spacecraft humanity has ever built, it took decades to reach its outer boundary. The heliosphere is a bubble, roughly spherical, carved out of interstellar space by the solar wind, the constant stream of charged particles that the sun pumps outward in all directions at hundreds of kilometers per second. This stream of particles is so energetic and so continuous that it pushes back against the interstellar medium, the thin gas and dust and cosmic radiation that fills the space between star systems, and creates a kind of protected zone centered on the Sun. Everything inside that bubble is, in a meaningful sense, inside the Sun's influence. The heliosphere dampens the intensity of cosmic rays, high-energy particles that stream in from the galaxy at large, produced by supernovae and other violent events in the interstellar medium. Inside the heliosphere, cosmic ray exposure is significantly lower than it would be in open interstellar space. The bubble is not impermeable. Some cosmic rays get through, but it provides genuine and substantial protection. Without the Sun, the solar wind stops. And without the solar wind, the heliosphere collapses. It would not happen instantly. The heliosphere is large enough that its collapse would take time. The outer edges of the bubble would begin to fade first, and the inward contraction would propagate at the speed of the solar wind, which means it could take years for the full extent of the heliosphere to disappear. But disappear it would, and in doing so, it would expose every planet in the solar system, including Earth, to the full intensity of the interstellar cosmic ray environment. This is not immediately catastrophic for a planet with a thick atmosphere and a magnetic field. Earth's own magnetosphere provides some protection against charged particles. It is what causes the aurora borealis and aurora australis, the magnetic field deflecting incoming particles toward the poles. But the magnetosphere is shaped partly by its interaction with the solar wind, and without that pressure, its structure changes. It expands into a different configuration, one that has existed only in theoretical models, without the constant stream of solar particles to push against and define its outer boundary. More cosmic radiation would reach the surface. For the last surviving humans in underground habitats, this is one more thing to engineer against: additional shielding, additional monitoring, additional complexity in an already maximally complex situation. For the frozen, lifeless surface, it barely matters. But for the deep biosphere, for the microbial communities in the deep rock and the deep ocean, the increased radiation is a new and unfamiliar stress on systems that evolved under the heliosphere's protection. Out in space, away from any planetary surface, other changes are underway that are quieter but no less real. Comets, those ancient travelers from the outer solar system, would lose their most dramatic feature. A comet in normal circumstances has two tails, one made of dust, one made of ionized gas, called an ion tail. The ion tail is created by the solar wind. As the solar wind streams past the comet, it interacts with the gases evaporating from the comet's surface and sweeps them away in a long, glowing stream that always points away from the sun regardless of the comet's direction of travel. It is one of the most beautiful sights in the solar system, a ghostly blue streamer of ionized gas trailing millions of kilometers through space. Without the solar wind, comets lose their ion tails. They might retain a dust tail, produced by the radiation pressure of sunlight itself pushing dust particles away from the nucleus. But radiation pressure also disappears with the sun's light, so even that would fade. Comets in a sunless solar system would be bare nuclei, dark, rocky, icy objects moving through space without the luminous displays that made them objects of wonder and sometimes terror to human observers throughout history. invisible, silent, just rocks in the dark. The solar radiation pressure that shapes the ion tails also acts on the smallest particles in the solar system, the fine dust and tiny debris that fills the inner solar system in a thin haze, the material responsible for the faint glow called the zodiacal light that can sometimes be seen after sunset or before sunrise from dark locations. That dust is constantly being pushed and sculpted by radiation pressure, its distribution shaped by the balance between the sun's light pushing outward and gravity pulling inward. Without that pressure, the dust settles differently. The zodiacal light fades, there is no light to scatter off it anyway, and the distribution of fine particles in the inner solar system gradually changes as gravity, no longer balanced by radiation pressure, becomes the dominant force on the smallest objects. Mars and Venus, too, feel the change. The solar wind has been stripping the upper atmospheres of both planets for billions of years, Mars dramatically so, since it lost its planetary magnetic field early in its history and has been slowly losing atmosphere ever since, a process driven in large part by the solar wind. Without the solar wind, that stripping slows and eventually stops. The thin, cold atmosphere of Mars is no longer being eroded. Not that this helps Mars in any immediate way, it is already too cold and too thin to be hospitable, and without the sun's warmth, it becomes colder still. But the process of atmospheric loss that has been running for 4 billion years simply stops, because the mechanism that drove it is gone. The solar system, in the absence of its star, becomes a quieter and stranger place. The planets continue their orbits, for a time. Gravitational interactions between the planets, freed from the dominant influence of the sun's mass, become more complex and eventually disruptive. Over very long timescales, without the sun's gravity to stabilize the system, planetary orbits could become chaotic. But that is a story for a much longer timeline than the one we have been tracing tonight. For now, the solar system is simply dark. The planets are dark. The comets are dark. The dust is settling. The heliosphere is fading at its edges. The cosmic rays are beginning to find their way in from the interstellar medium, slow and relentless, like water finding the cracks in a wall. The boundary between the solar system and the rest of the galaxy, which was once clearly defined by the edge of the heliosphere, is becoming indistinct. The protected zone that our sun maintained for billions of years, the zone inside which life on Earth developed, sheltered from the harshest of what the galaxy can produce, is dissolving. What remains is a collection of cold bodies moving through open interstellar space, no longer a solar system in any meaningful sense, just matter, ancient, complex, carrying within it the record of everything that happened here, moving outward into a galaxy that is full of other stars and other stories and other warm pockets of possibility. The Earth is still there. Still moving. Still carrying, in its deep rock and deep ocean, the last traces of life that a star made possible. Still turning, still cold, still dark. And the stars, as always, are everywhere. There is a kind of cold that exists beyond anything living experience can prepare you for. We have frameworks for cold, the sting of a winter morning, the numbness of bare hands in snow, the deep bone chill of a particularly brutal night. We have measurements for the extremes of our world, the coldest temperature ever recorded on Earth's surface was around -89 degrees Celsius, measured in Antarctica. We know that Mars reaches -73 degrees in its polar winters. We know that the surface of Pluto, that small and distant world at the edge of the solar system, sits around -230 degrees Celsius. These numbers are part of a spectrum that has a hard lower limit. Absolute zero, -273.15 degrees Celsius, is the temperature at which all thermal motion stops, the point beyond which physics does not allow temperature to fall. It is a theoretical boundary, an asymptote that matter can approach but never quite reach. In the very long term, a sunless Earth moves along that spectrum. Slowly at first, then faster as the insulating effects of the atmosphere and the ocean diminish, then slowly again as geothermal heat provides a floor against the deepest cold. But the direction is always the same. Down. Toward a cold that has no name in human experience. And as the temperature descends through stages that have no precedent in Earth's history, the atmosphere itself begins to change in a way that is almost impossible to fully visualize. Gases condense. This is a fact of physics so basic that it seems almost too simple to be significant, but its implications, in the context of a cooling planet, are extraordinary. Every gas has a temperature at which it transitions from vapor to liquid, and a lower temperature at which it freezes into a solid. Water vapor becomes liquid water at 100 degrees Celsius and ice at 0. Carbon dioxide, the greenhouse gas, the byproduct of breathing and burning, becomes a liquid around -78 degrees Celsius at atmospheric pressure and then a solid, dry ice, at temperatures not far below that. Earth's atmosphere is mostly nitrogen. About 78% of every breath is nitrogen, a stable and unreactive gas that forms the invisible background of the air around us. We rarely think about nitrogen because it does not do much in normal atmospheric chemistry. It does not burn, it does not cause acid rain, it does not warm the planet. It is simply there, making up the bulk of the air by volume. Nitrogen condenses at -196 degrees Celsius. As Earth continues to cool toward and beyond that threshold, and in the extreme long-term models, some projections suggest temperatures reaching -219 degrees Celsius or lower, nitrogen stops being a gas. It liquefies first, raining down as a thin, colorless liquid onto the already frozen surface. Then, as the temperature drops further, it freezes. The main component of Earth's atmosphere, the invisible gas that has surrounded this planet for billions of years, falls out of the sky and joins the ice. The atmosphere does not disappear all at once. Different components condense at different temperatures, so the process is staged. Carbon dioxide goes first, relatively early in the cooling timeline, forming dry ice on the surface, a layer of frozen carbon dioxide accumulating on top of the water ice that is already there. The greenhouse effect, already weakened by the loss of solar input, fades further as CO2 is removed from the air. This accelerates the cooling, because what little heat was still being trapped by the greenhouse effect is now escaping more freely into space. Then, as temperatures drop further, other components of the air begin to follow. The atmosphere thins. The surface pressure drops. The sky, which once held complex weather systems and dramatic cloud formations, becomes increasingly bare, not empty of gas, but holding far less of it, the pressure falling towards something approaching a near vacuum at the surface. Eventually, with nitrogen condensing out of the air and the temperature approaching the most extreme cold that physics allows on a planetary surface, the precipitation that falls on Earth is no longer water-snow. The clouds that form, if they form at all, are not water clouds. They are oxygen clouds. Oxygen snow falls on a surface already covered in layers of frozen water, frozen carbon dioxide, and frozen nitrogen. The world's surface, at this stage, looks nothing like anything that existed before. It is layered ice, different compositions at different depths, a geological record of the atmosphere falling in stages, like pages of a book settling onto a surface one by one. A record, written in ice, of what the air once was. The surface pressure is almost nothing. The sky is almost completely black, even in the metaphorical daytime, because there is almost no atmosphere to scatter or absorb anything. The stars are visible with a clarity that would be extraordinary if there were eyes to see them. Every star in the visible universe, sharp and steady and entirely indifferent, looking down on a surface that is as alien as any world we have ever imagined. And beneath all that layered ice, beneath the frozen atmosphere and the frozen oceans and the frozen surface, the deep rock still holds some warmth. The geothermal heat is still rising, still faint, still maintaining the minimum conditions for the deepest microbial life in the narrow zones close enough to the heat to benefit from it. How long that persists is uncertain. It depends on the rate of radioactive decay in the mantle, on the residual heat of the planet's formation, on factors that play out over timescales measured in billions of years. But eventually, even that fades, and the planet becomes fully cold. A frozen, airless, dark body drifting through space, carrying within it, buried deep in its layered structure, the frozen record of everything it once was. This is what it means to become a rogue planet. The term sounds dramatic, and perhaps it is, but it is also simply descriptive. A rogue planet is any planetary mass body that moves through space without being gravitationally bound to a star. They exist throughout the galaxy in enormous numbers. Some estimates suggest there may be billions of rogue planets in the Milky Way alone, worlds that were once part of planetary systems and were ejected by gravitational interactions, or worlds that formed in isolation from collapsing gas clouds and never had a star to orbit in the first place. Most rogue planets are cold. Most are dark. Most are, as far as we can tell, lifeless, though the question of whether some of them might harbor life in deep oceans kept liquid by internal heat is one that scientists take seriously. Some rogue planets are gas giants, enormous worlds that carry their own internal heat from formation and might maintain liquid layers in their depths for billions of years. Others are smaller, rocky, more like our Earth, and those are, in the absence of internal heat, simply frozen rocks moving through the interstellar medium. Earth, in this scenario, joins them. It crosses the boundary between a planet and a rogue world not in a single moment but gradually, as the influence of where the sun was fades to irrelevance and the pull of the interstellar medium and the gravitational influences of other stars begin to dominate. It is no longer the third planet from a star. It is no longer part of a system at all. It is a body in motion through the galaxy, following a path determined by its velocity at the moment the sun disappeared and by every subsequent gravitational interaction it encounters. At 108,000 kilometers per hour, it moves steadily through the dark, not toward anything in particular. The nearest star system, Alpha Centauri, is about 4.2 light-years away, a distance so large that even at Earth's current speed, the journey would take roughly 37,000 years. And Alpha Centauri is not in the direction Earth is heading anyway. The path leads somewhere else, somewhere unnamed, through a region of the galaxy that is mostly empty in the way that most of space is mostly empty. Enormous distances between anything of significance, the occasional gas cloud, the very occasional other rogue planet passing at a distance of several light-years. The Earth that makes this journey is not the Earth we know. It is a frozen sphere, layered with ice of multiple compositions, its surface buried under the remnants of its own atmosphere, its oceans locked solid, its continents as cold and airless as any barren moon. The familiar geography is still there, underneath, the shapes of the continents, the basins where the oceans were, the mountain ranges, but buried, preserved in ice, a fossil of a living world. There is something both melancholy and beautiful about the image of a rogue Earth moving through the galaxy. Melancholy because of everything that is gone, the life, the warmth, the extraordinary complexity that 4 billion years of solar energy and biological evolution produced. Beautiful because the planet itself persists, carrying that record, moving through the universe as a kind of frozen archive of everything that happened here. Every species that ever lived on this planet left some trace in the rock. The fossil record, the chemical signatures in the sediment, the layers of the geological column, all of it is still there, beneath the ice, preserved with extraordinary fidelity by the cold that killed the surface. A researcher from another civilization, finding this frozen world a billion years from now, could in principle read the history of life on Earth and its rocks. Could find the signatures of photosynthesis, the oxygen atmosphere, the complex ecosystems, the rapid chemical anomalies of industrial civilization. Could piece together, from the frozen evidence, the story of a world that once had a star and made extraordinary use of it. The Earth does not forget. Even frozen, even dark, even drifting alone through the interstellar medium, it carries its history with it. Rogue planets, when they wander long enough, sometimes encounter new star systems. The gravitational influence of a passing star could, over very long timescales, alter the trajectory of a rogue planet, drawing it into a new orbit, warming it, perhaps, after billions of years of cold. This is extraordinarily unlikely for any given rogue planet in any given time frame that feels meaningful. The galaxy is too large, the distances too vast, the encounters too rare. But it is not impossible. The universe is patient in ways that make human timescales feel like a single heartbeat. A frozen Earth, in a billion years, in a galaxy that continues to evolve and change and occasionally bring things together that were long apart, there is a very small but real possibility that it meets a new star. That it enters a new orbit. That sunlight, or starlight from a different sun, falls on its frozen surface and begins, very slowly, the process of warming. Whether anything survives to be warmed by that new light, Whether the deep microbial life in the rock holds on through the billions of years of cold is genuinely unknown. Life is more durable than it looks, and the deep rock of a planet can insulate against cold for an extraordinarily long time. It is not impossible. It might even be, by the standards of probability in a galaxy of hundreds of billions of stars, less unlikely than it seems. But that is a story for another day. A much longer day, in a much older galaxy. For now, the Earth moves. Cold and dark and carrying everything it ever was, it moves through the space between the stars at the speed it has always had, 108,000 kilometers per hour, in the direction it was going when the sun left. The stars are everywhere around it. Some of them have their own planets, their own warmth, their own biospheres doing what Earth's biosphere once did, capturing starlight, building complexity, making life out of chemistry and time. The galaxy is full of these small pockets of warmth and improbability, scattered across distances that would take lifetimes to cross. Earth passes among them, not stopping, not arriving, just moving, a traveler with no destination, carrying the memory of a living world in its frozen layers, moving through the long dark of the universe with the quiet dignity of something that endured for as long as it could, and is still, somehow, here. The stars watch. The cold continues. And the rogue Earth, patient and dark and extraordinary in its frozen completeness, goes on. The word dead is one we use carefully when talking about planets. It carries a weight that implies something was once alive, and in Earth's case, that is not a metaphor. Earth was alive, in the fullest and most literal sense. It hosted life. It was transformed by life. Its atmosphere, its oceans, its surface chemistry, its very rocks, all of it was shaped, over billions of years, by the presence and activity of living organisms. The oxygen in the air was put there by cyanobacteria. The limestone in the cliffs was built from the shells of ancient marine creatures. The coal seams underground are the compressed remains of ancient forests. A dead Earth, drifting through interstellar space, carries all of that history in its structure. It is not simply a rock. It is a record. A frozen, dark, airless archive of what 4 billion years of life in chemistry and geology can produce when a planet sits at the right distance from a stable star for long enough. But it is, in every functional sense, dead. The warmth is gone. The motion of the surface, the plate tectonics, the volcanic eruptions, the mountain building and erosion that have continuously reshaped the surface throughout Earth's history, has slowed to almost nothing and will eventually stop as the interior cools over billions of years. The water cycle is frozen. The atmosphere is condensed on the surface. The life that persisted longest, in the deepest rock in the deepest ocean, has finally reached the limit of what geothermal heat can sustain, and the chemistry has gone quiet. What drifts through the interstellar medium is complete. Finished. A world that ran its full course and is now simply moving, as things in space do, because there is nothing to stop it. And it is not alone out there. Because the sun's disappearance did not only affect Earth. Every body in the solar system, every planet, every moon, every comet, every asteroid, every grain of dust held in its current distribution by the balance of solar gravity and radiation pressure, is affected simultaneously and completely. Jupiter, the largest planet in the solar system, more than 1,000 times Earth's volume and containing more mass than all the other planets combined, loses its gravitational anchor. Saturn, with its extraordinary ring system, rings that exist because of the delicate interplay of gravitational forces in a stable solar system, loses the organizing influence that kept it in its predictable orbit. Uranus and Neptune, the distant ice giants at the outer edge of the planetary system, were already barely within the Sun's warmth. They drift outward, or sideways, or in whatever direction their orbital velocity at the moment of the Sun's disappearance takes them. The solar system, as a system, ceases to exist almost immediately in any meaningful dynamical sense. Without the Sun's overwhelming gravitational dominance, remember that 99.8% of the system's mass, the remaining bodies interact with each other in ways that become increasingly chaotic over time. The gentle, stable, nearly circular orbits that the planets have maintained for billions of years were never self-sustaining. They were sustained by the Sun. Without it, they are just vectors. Velocities. Directions of travel that will be gradually modified by every gravitational encounter that follows. Jupiter and Saturn, by virtue of their enormous mass, will continue to influence each other and the smaller bodies around them for a very long time. Their mutual gravitational interactions could pull smaller planets into new trajectories, potentially toward each other, potentially outward into the interstellar medium, potentially into close encounters that would have been impossible in the organized solar system. The asteroid belt, already a collection of bodies whose orbits were shaped by Jupiter's influence, becomes a more chaotic place. Asteroids that were held in relatively stable resonances with Jupiter's orbit find those resonances disrupted. They drift. They wander. Over long timescales, some of them will collide with planets or moons. Others will be ejected from the former solar system entirely. Comets from the outer reaches, from the Kuiper belt beyond Neptune and the distant Oort cloud at the very edge of the solar system's gravitational reach, are among the first to feel the change most profoundly. They were already only loosely bound to the Sun, their orbits stretching out to extraordinary distances where the Sun's gravity was barely stronger than the gravitational influence of passing stars. Without the Sun's gravity at all, many of them are simply free. They continue in whatever direction they were moving, dispersing into the interstellar medium over time, joining the population of interstellar objects that drift between star systems. Earth, on its straight-line path through space, is now just one more object in a former solar system that is gradually dispersing. The organized, structured, elegantly clockwork arrangement of planets and moons and smaller bodies, one of the most stable planetary systems we know of, is dissolving into a loose collection of independent travelers, each one going somewhere different, none of them with a destination. Over very long timescales, some of these travelers will have encounters. Earth, moving through interstellar space, is not immune to gravitational interaction. The galaxy is not truly empty, it contains gas clouds, other rogue planets, and occasionally the gravitational influence of passing stars. Any of these could, over millions or billions of years, alter Earth's trajectory. A passing star close enough could deflect Earth's path significantly. A particularly massive gas cloud could slow it slightly. Over billions of years, the cumulative effect of these interactions could take Earth in directions that no calculation made at the moment of the Sun's disappearance could predict. And then there is the possibility, remote, but real, of capture. If Earth's path through the galaxy brings it close enough to another star system, and if the geometry of the encounter is right, Earth could be gravitationally captured into an orbit around a new star. This is not a common event. It requires a specific and unlikely set of circumstances, the right relative velocities, the right distance of closest approach, often the involvement of a third body to carry away the excess energy that capture requires. But the galaxy is old and large, and over billions of years, rare events occur. A captured Earth around a new star would begin, very slowly, to warm. The ice on the surface would begin, over millions of years, to melt, first on the side facing the new star, then gradually more broadly as the planet's thermal equilibrium shifted. Whether anything survived in the deep rock to respond to that warming is, as we've discussed, genuinely uncertain. But the possibility that a frozen Earth, warmed by a new star after billions of years of cold, might see some form of chemical resurrection, some reawakening of the chemistry that once produced life, is not zero. The universe has done stranger things. There is something important to step back and acknowledge at this point in the story, something that all of these facts, taken together, make undeniable. The sun is not simply a light source. It is not just the thing that makes days bright and plants grow. It is the organizing principle of the entire solar system. It is the source of virtually all the energy that flows through every ecosystem on Earth. It is the gravitational anchor that holds every planet in its path. It is the producer of the solar wind that shapes the space environment around every planet for billions of kilometers in every direction. It is the creator of the heliosphere that protects the system from the harshest radiation in the galaxy. It drives the water cycle, the weather, the climate, the seasons. It regulates the biological rhythms of nearly every living thing on the planet. It provides the ultraviolet light that makes vitamin D in skin and sterilizes surface water and shapes the chemistry of the upper atmosphere. Remove it, and everything changes. Not some things. Not most things. Everything. This is not a small observation. It is a statement about the nature of the relationship between a star and its planetary system, a relationship so total and so fundamental that it is almost impossible to see clearly from inside it. We are so immersed in the sun's influence, so completely shaped by it at every level from the molecular to the civilizational, that its presence is invisible to us in the way that water is invisible to fish. It is the medium we exist in. The condition that everything else depends on. The thought experiment of its absence is valuable precisely because it makes visible what is normally invisible. It illuminates the structure of the relationship by imagining its removal. And what it shows is a dependence so complete, so layered, so woven into every system and every organism and every process on this planet, that the word profound barely begins to cover it. We live on a planet that a star made possible. Not just comfortable, possible. The star did not merely provide pleasant conditions. It created the conditions. It organized the system. It sustains, every day, the energy flows and chemical balances and gravitational structures that allow complexity to exist. And it will continue to do so for approximately another 5 billion years. This is where the story takes an unexpected turn, because the sun, like all stars, has a finite life. It is burning through its hydrogen fuel at a measured rate, and eventually, billions of years from now, that fuel will run low. The sun will change. It will expand into what astronomers call a red giant, swelling to many times its current size, its outer layers expanding outward through the inner solar system. Mercury will be engulfed. Venus almost certainly will be. And Earth? The fate of Earth when the sun becomes a red giant is, remarkably, not fully settled. For a long time, the conventional understanding was that Earth would be consumed, swallowed by the expanding outer layers of a dying star, destroyed in the most complete way imaginable. And that may still happen. The sun will lose mass as it expands, and as it loses mass its gravitational pull will weaken slightly, which will cause Earth's orbit to shift outward, potentially moving Earth just far enough to stay ahead of the expanding stellar envelope. Some studies suggest that under certain conditions, depending on exactly how much mass the sun loses and how quickly, depending on tidal interactions between the expanded sun and Earth's orbit, Earth could survive the red giant phase. Not comfortably. Not in any way that supports life. The heat would be extraordinary, the surface would be scorched and molten, the atmosphere as we know it would be long gone. But the planet itself, the rocky body, might persist. Might survive as a scorched, airless rock in an orbit around a dying star, waiting for the next phase, the eventual collapse of the sun into a white dwarf, a dense and slowly cooling ember of what was once a star. A white dwarf orbited by a surviving Earth. It is a strange image. Cold and dim, the former sun radiating only faint heat across a distance that was once the distance from the Earth to a living star. Earth, in this scenario, might be habitable in a very different sense, close enough to a cooling white dwarf that some warmth reaches it, in a universe that is itself much older and cooler than the one we know. But that is speculation about the far end of a very long story. Tonight's story has been about a different kind of ending, the sudden kind, the imagined kind, the thought experiment that strips away the star and asks what remains. What remains is a planet. Frozen, dark, and extraordinary in its frozen completeness. A record of life. A testament to what is possible when a rocky world sits at the right distance from a stable star for 4.5 billion years. A story written in rock and ice and the layered chemistry of what was once an atmosphere. The solar system that organized itself around one star's gravity has dispersed into the galaxy, each body going its own way, none of them the same as they were, all of them carrying forward the momentum of a system that once worked together with extraordinary precision and elegance. And somewhere in the dark, among the stars, of which there are hundreds of billions in this galaxy alone, each one a sun, each one potentially holding its own planets in its own warm embrace, the frozen Earth continues its journey. Patient. Complete. Going somewhere unplanned in a universe that is larger and older and stranger than any thought experiment can fully contain. The stars are everywhere. The dark is vast. And the sun, whose absence we have been imagining all this time, is right where it has always been, burning steadily, pulling the planets in their orbits, warming the surface of a living world, rising tomorrow as it has risen for 4.5 billion years. It is ordinary. It is extraordinary. And tonight, perhaps for the first time, it is possible to see it clearly for what it is. Everything,